Okay, good afternoon, all of you. In today's session, we are going to do the chapter waves. So, in waves, we are going to begin with mechanical waves, that means waves on a string. So, suppose let us say that there is a string which is fixed at one end to the wall. Okay, there is a string, so at one end it is fixed to the wall. Okay, it is rigidly fixed to the wall, and the other end it is free. Okay, there is a string at one end, the string is fixed to a wall, and at the other end the string is free. So over here the string is free. So the person who is holding the string in his hand, that person gives a sudden sharp jerk to the string. Okay, the person who is holding the string, he gives a sudden sharp jerk to the string, and that sudden sharp jerk will result in the formation of a pulse. Okay, it will result in the formation of a pulse, and a pulse is basically symbolic of energy that has been imparted to the string, because the string was absolutely flat, and then this person gave a sudden sharp jerk, and that is why you had a pulse. Okay, so pulse is symbolic of what energy has been imparted to the string, and then the pulse will travel towards the wall. Okay, so the pulse will travel towards the wall. So basically, when the time is 0, okay, when the time is 0, the free end of the string, let us say that it is x equal to 0. So when time is 0, then the free end of the string, the location is x equal to 0. And suppose let us say that the pulse is moving down, and at a time t we are at a position x. Okay, so at the time 0 the pulse has just been created, and the place where the pulse has just been created, we are calling it as x equal to 0, and at a time t the position, we are calling it as x. So okay, now this pulse, which is located at x comma t, like the location of the pulse is x and the time is t. So this pulse was at the free end at some time. Okay, at some time this pulse was at the free end. So when was this pulse at the free end? At time t minus x by v. V is the speed of the pulse. Okay, v is the speed of the pulse. So v is the speed of the pulse. So the pulse which is over here, it was at the free end at time t minus x by v. Now the other thing that we are interested is the shape of the pulse. So I have just drawn a arbitrary shape. Okay, I have just drawn one arbitrary shape, which is a very non-specific shape. But what about the shape of the pulse? Okay, so the shape of the pulse, we will expect that it will be some function of location and time. But what function, we don't know. But it will be some function of location and time. So we can say that we can say that the equation of the pulse will be yx comma t is f of t minus x by v. Okay, the equation of the pulse yx comma t is function of t minus, this is the equation of the pulse, because like I said, at position x and time t, the pulse is over here. That means the pulse was at the free end at time t minus x by v, and therefore the equation of the pulse, we can say y x comma time is f of t minus x by v. So this is the first equation of this chapter, that is equation of the pulse, right? Now one very important thing is that the person has given the string a jerk, and then he is just holding the string in his hand. So the person who is handling the string, he gave the string a jerk, and after that he is just holding the string in his hand. So because he is just holding the string in his hand, so you will only have one pulse, and after that you will not have anything else. But suppose if that person, he continuously jerks the string, okay, in a systematic manner, then you will get a succession of pulses. So if this person keeps jerking the string in a systematic manner, then you will get a succession of pulses, okay. That succession of pulses is called a wave, right? So the person gave a sudden sharp jerk, and then he just held the string in his hand, so then you will just get a pulse. But suppose if he systematically goes on jerking the free end of the string, then you will get a succession of pulses, and a succession of pulses is called a wave. But in what way will he jerk the string, that has to be known, okay. So he is giving jerks to the string, that is okay, but what is the manner in which he is jerking the string, that we need to know. So in the syllabus of all the exams, whether it is the school exam or any competitive exam, whether it is JEE or KVPY or NEET or whichever, the only kind of systematic jerking of the string which is there, that is simple harmonic motion. So if the free end is jerked in simple harmonic motion, so suppose if the free end of the string is jerked in simple harmonic motion, okay, this is the free end. Suppose you are jerking the free end in simple harmonic motion, so the equation will be ft equal to a sine omega t. This will be the equation of the free end, and you know a sine omega t is a typical displacement equation of simple harmonic motion. So the person is jerking the free end in simple harmonic motion, and the equation is given by ft equal to a sine omega t. So in that case, the equation of the wave, it will be y is equal to function of t minus x by v, and since the free end is ft equal to a sine omega t, so function of t minus x by v will be a sine omega into t minus x by v. So the equation of the wave will be a sine omega into t minus x by v. So this is the first formula of this chapter, okay. Equation of wave is y equal to a sine omega into t minus x by v. So that means that if the person jerks the free end in a simple harmonic motion, then instead of getting a pulse, you will get a succession of pulses, succession of pulses is called a wave, and the equation of the wave will be y equal to a sine omega into t minus x by v. And one more thing is that if you open this bracket a sine, if you open this bracket, so omega into t you will get, and then omega into x by v. So omega into t minus omega x by v. So there is something called wave number. Okay, so this is another formula equivalent of the first formula. Suppose if I say a sine omega t minus omega x by v, then omega, you know very well from simple harmonic motion knowledge, omega is called angular frequency. So angular frequency is 2 pi by time period, and 1 by time period is the frequency. So 2 pi by time period is 2 pi into frequency. And what is k? K is called wave number. By the way, what is wave number? It is 2 pi by wavelength. Okay, what is the definition of wave number? It is 2 pi by wavelength. And you have now also seen that wave number can be written as omega by v. Okay, so capital A is the amplitude, omega is the angular frequency, which is 2 pi by time period or 2 pi into frequency. K is the wave number, which is 2 pi by wavelength or omega by v. Okay, and of course there is another formula. So y equal to capital A into sine 2 pi by capital T into small t minus 2 pi by lambda into x. So this is another formula, another version of this formula. Capital A sine 2 pi by capital T into small t minus 2 pi by lambda into x. So this is another version. This is number 3. Okay. So these three, this is number 1, this is number 2, this is number 3. These three, they are the three forms of the wave equation. So the wave equation has three formulas, and these are the three formulas. Okay, now we come to number 4, velocity of a wave on a string. Okay, formula number 4, velocity of a wave on a string. So velocity of a wave on a string, the formula is V equal to root over T by mu. T is the tension, okay, and mu is the mass per unit length. Now this formula has a derivation, but I'll not do the derivation. It's a very cumbersome, very big derivation, and it isn't worthwhile trying to remember that derivation. So velocity of a wave on a string. So I had told you when we were discussing the person is jerking the string, that time I told you that if he jerks the string in simple harmonic motion, then you will get a succession of pulses, which is basically a wave which will go towards the wall, and the velocity of that wave will be root over T by mu. So T is the tension and mu is the mass per unit length. Then we come to number 5. Then we come to number 5, average power transmitted across a string. So average power transmitted across a string, the formula is 2 pi square mu into V into capital A square into F square. Okay. So average power transmitted across a string. So you know that when a pulse or a wave is transmitting down a string, it is basically energy in motion. So you know that the rate at which energy is transmitted down the string, that is power, and you know that the entire thing is happening in a variable way. So if you calculate the power, the energy transmitted in one time period divided by the time period, so that is the average power transmitted across a string. So it will be 2 pi square into mass per unit length into speed of the wave into amplitude square into frequency square. This is the formula. Okay. Now we come to the next concept, that is interference of waves. That is the next concept. Now, what is the primary difference between the meeting of two waves and the meeting of two particles? You see, when two particles meet each other, what happens is there is a collision. There is a collision, and you know that collision can be of different types. It is elastic, inelastic, etc. But when two waves meet each other, then normally what happens is something called interference. So interference means that the two waves will meet each other and they will create a resultant wave. So suppose the wave is A1 sine kx minus omega t and the other wave is A2 sine kx minus omega t plus delta. Suppose these are the two waves. So when these two waves meet each other, so they will create a resultant wave, that is y equal to y1 plus y2. So the resultant amplitude will be A, then sine kx minus omega t plus, there will be a figure epsilon, okay, kx minus omega t plus epsilon. So A will be root over A1 square plus A2 square plus 2A1 A2 cos delta, right? So A is equal to root over A1 square plus A2 square plus 2A1 A2 cos delta. And this is the resultant amplitude. So the two waves have met each other, they have created a new wave. The amplitude of the new wave is A, and A is root over A1 square plus A2 square plus 2A1 A2 cos delta. And this new phase angle epsilon, tan epsilon, is A2 sine delta by A1 plus A2 cos delta. So these are the details of the new wave which has been created. But there is a condition. There is a condition. What is that? These two waves, they must be coherent. Okay, these two waves, they must be coherent. Coherent means that this phase difference delta, it should be constant. It should not keep changing. So the phase difference between the two waves, that is delta, it should be a constant. If delta is a constant, then we say that these two waves are coherent. And if the two waves are coherent, then only interference will happen. Only then interference will happen. So the phase difference delta, it has to be a constant. And if delta is a constant, then interference will happen. That means the two waves will overlap to create a resultant wave. If delta is not constant, suppose, then what will happen? The two waves will meet each other and they will just pass over each other as if nothing has happened. So you will not get any observable phenomenon. They will just meet each other and pass by. After meeting each other, the very next moment they will just pass by as if nothing has happened, which is unlike collisions. Again, in collisions, when the two bodies collide, they definitely do something to each other, they exert a force on each other, there's a change in velocity. So in interference, if delta is constant, the two waves are coherent, then they will have a resultant wave, and the resultant wave amplitude is this, epsilon is this. By the way, the technique by which the resultant wave is obtained, that technique is called principle of superposition. Okay, so the technique by which the two waves will overlap with each other to give a new wave, that technique is called principle of superposition. So this is the new wave, this is the amplitude, and this is the epsilon. So this is known as principle of superposition. Okay. So cos delta is plus 1. So that is the maximum value of cos delta, that is plus 1. So then we say that the two waves are interfering constructively. So if cos delta is plus 1, it is constructive interference. And for what angle is the value of cos plus 1? The angle will be multiple of 360, so 2 and pi. And if cos delta is minus 1, it is called destructive interference. So for what angle will the two waves interfere destructively? So the answer is that it is multiple of 360 plus pi. So delta will be 2n plus 1 into pi. So if the resultant amplitude is maximum, then the two waves are said to interfere constructively, and cos delta is plus 1, delta is 2n pi. If the resultant amplitude is minimum, the two waves are said to interfere destructively. So cos delta is minus 1, delta is 2n plus 1 into pi. Okay, the next thing is, suppose a pulse is traveling towards the wall. Suppose a pulse is traveling towards the wall. So the pulse will hit the wall, and at the wall we are not supposed to have any displacement, right? So if the pulse is hitting the wall, then at the wall we are not supposed to have any displacement. But the fact is that there is a pulse which is a carrier of energy which is hitting the wall. So the explanation given by the scientist was that the pulse is hitting the wall, and this is the incident pulse, and whatever is rebounding from the wall, that is the reflected pulse. So this is the incident pulse, this is the reflected pulse. Now the explanation given was the reflected pulse will be inverted with respect to the incident pulse. So if you combine these two, this is the incident and this is the reflected, if you combine these two, then at the wall you will get zero displacement. So this was the explanation given by the scientists, that in case of reflection, the explanation which they gave was that there will be one incident pulse, okay, that is going to hit the wall. The reflected pulse is going away from the wall, and this will be inverted with respect to the incident, so that the combination of both of them on the wall will give a zero displacement. That means in case of pulse or a wave, the reflected is inverted with respect to the incident. Okay, now this is the incident pulse, this is the reflected pulse. If you have, instead of a wall, if you have a wire on which a ring can slide freely up and down. So this is a wire, and on this wire this ring can freely slide up and down. In that case, the incident pulse and reflected pulse, they will be identical, they will not be inverted with respect to each other. And by the same concept that was applied here, on the wire the resultant amplitude will be the total of these two. So whatever is this and whatever is this one actually will be double of either, right? So on the wire, the pulse will be double of either. It will be double of both this and this, right? So this will be the thing. Okay, now whatever I told you about reflection and transmission of pulses, let us see how we can apply that to a system of combination of wires or combination of strings. So suppose there is a very thin string and over here there is a much thicker string. So this is a thin string, this is a thick string. So if a pulse is traveling down the thin string, it will reach this point, and after reaching this point, a part of it will be reflected and a part will be transmitted. Transmitted in light, we call it refracted. So what will happen is that according to whatever we have understood up till now, the reflected pulse, it will behave as if the thick string is a rigid obstacle. So this is the incident pulse, the reflected pulse will behave as if this is a rigid obstacle, and if this is a rigid obstacle, then the reflected will be inverted with respect to the incident, but the transmitted will be exactly identical to the incident. So this is the first scenario. The second scenario is that suppose the thick string is first and the thin string is later, suppose. So the pulse is going over the thick string, and when it reaches the the boundary of the two strings, so this will be the reflected and this will be the transmitted. So here the reflected and the original will be in the same phase, and the transmitted will also be in the same phase as the original, simply because this time the string which is in the latter part, it is a thin string, so it is acting like a ring moving on a sliding wire. So because the latter half is a thin string, so it will behave like a ring moving on a sliding wire. So this is the topic, reflection and transmission of waves. Okay, so y1 is a sine kx minus omega t, and y2 will be equal to a sine kx minus omega t plus delta. Okay, so y1 is a sine kx minus omega t, and y2 is a sine kx minus omega t plus delta. So these are the two waves. Okay, kx plus omega t. So these are two waves. One of them is moving towards the rigid obstacle, that is, say suppose a wall. Okay, the other one is reflected and going back. So one of them is going towards the wall, the other one is reflecting and coming back from the wall. So these are the two. So when these two interfere, so it will be a into sine kx minus omega t plus sine kx plus omega t plus delta. So 2a sine kx plus delta by 2 . So 2a sine kx plus delta by 2 cos omega t plus delta by 2. So this is sine plus sine, so this will be the resultant. 2a sine kx plus delta by 2 cos omega t plus delta by 2. Okay. Okay, now suppose we are talking about a string and this is the fixed end of the string. So at the fixed end of the string the position is 0 and the displacement will be 0 because it is fixed. So x will be 0 and y will also be 0. So since since x will be 0 and y equal to 0, so therefore delta will be 0. Okay. So since x will be 0 and y will be 0, so that means delta will be 0. So then you will get y equal to 2a sine kx into cos omega t. Okay. So y equal to 2a sine kx into cos omega t. Now this y equal to 2a sine kx cos omega t, this is called standing wave. So y equal to 2a sine kx cos omega t, this is called a standing wave or a stationary wave, because if you draw the diagram of this, then this is the wave going to the right and and this is the wave going to the left. So if you draw the diagram, so you have a wave going to the right, you have a wave going to the left. And these two waves, when they, when you consider their superposition, you will get an impression that the overall thing is neither going right nor going left. You will get an impression that it is just standing at one place and flapping up and down. When you look at this diagram, the impression you get is, overall impression you get is, it is neither going right nor going left. It is at one place only, it is just flapping up and down. So that is why it is called a standing or a stationary wave. Now, if you see this equation of standing wave, if you put sin kx equal to 0, then kx will be n pi, that is called a node. Suppose if you put sin kx equal to 0, then kx will be equal to n pi, that is called a node. So the node is the position of zero displacement, okay? So if sin kx is 0, it is called a node, then kx is n pi. If sin kx is plus minus 1, it is called an antinode. Kx is 2n plus 1 into pi by 2. So node is the point of zero displacement and antinode is the point of maximum displacement, right? So if you now see this diagram, so I'll just draw it a little bigger. So this will be the diagram. So these points are the nodes. Okay, these points are the nodes because at these points there is no displacement. This one, this one, this one, this one, this one. These are the nodes. At these points there is no displacement. And these points, this one, this one, this one, this one. Okay, these points, they are the antinodes. So these are the nodes. 1, 2, 3, 4, 5. These are the nodes. And these vertical dash lines which I have drawn, these are the antinodes. So between a node and an antinode, the gap will be wavelength by 4. As you can see, it is wavelength by 4. So between a node and antinode, the gap will be wavelength by 4. Acha, between two nodes or two antinodes, the gap will be lambda by 2. Between these two nodes or these two antinodes, it will be lambda by 2, right? And so that is some of the important things about standing waves. So standing wave, it will give an impression that the wave is just flapping about a point, it is neither going right nor left. Standing wave equation is 2a sin kx cos omega t. In a standing wave, there are points of zero displacement, they are called node. So sin kx is 0, so kx is multiple of pi. In a standing wave, there are points of maximum displacement either up or down. They are called antinodes. So sin kx is plus minus 1, so kx is 2n plus 1 into pi by 2. And the distance between a node and an antinode is wavelength by 4. The distance between two consecutive nodes or two consecutive antinodes is wavelength by 2. So these are the details of standing wave. Now coming back to this diagram, so x is 0, y is 0, and x is 0, y is L. Okay, x is 0, y is 0, and x is 0, y is L. You have fixed both ends of the string. Suppose you have fixed both ends of the string. So the standing wave equation is this, but you have fixed both ends of the string. So so sin KL will be 0. So KL will be equal to n pi. So L will be n pi by k, that is n lambda by 2. So I am repeating again. So far I was telling you that the string one end is fixed, and then we discussed what happens when the incident and reflected waves, they superpose with each other, you get a standing wave. So far that is what we discussed. Now suppose the other end of the string also we fix it. So other end of the string, when x is L, y is 0. Because this is x equal to L and there is no displacement, y is 0. So in the standing wave equation 2a sin kx cos omega t, if I put x is L, then sin KL will be 0. So KL will be equal to n pi. So L will be n pi by k. So KL will be n pi and L will be n pi by k. So instead of writing pi by k, you write lambda by 2. So L will be n into lambda by 2. Okay, so this will be the answer. Now L is equal to n into lambda by 2 means that so if you put n equal to 1, then L will be lambda by 2. Okay? So if you put n equal to 1, then L will be lambda by 2. So that means the diagram will be like this. So this is called fundamental. So L will be lambda by 2. This is called fundamental. If you put n equal to 1, L will be lambda by 2. This is called fundamental. And lambda is velocity by frequency. So frequency is v by 2L. So that is 1 by 2L into root over tension by mu. So the fundamental frequency F is v by 2L. So 1 by 2L into root over tension by mu. This is the fundamental frequency. Okay. Now suppose if you put n equal to 2, so suppose if you put n equal to 2 over here, then L will be equal to lambda. And you know that lambda is V by F, so F will be 1 by L root over T by mu. So that is 2 by 2L root over T by mu. So this is called first overtone, it is also called second harmonic. Okay? So it is called first overtone, it is also called second harmonic. Now if you put n equal to 3, then L will be 3 lambda by 2, that is 3V by F. So F will be 3 by 2L root over T by mu. This is second overtone, third harmonic. So F is 2 by 2L root over T by mu. This is first overtone, second harmonic. And F is 3 by 2L root over T by mu. This is second overtone, third harmonic. And by the way, the second harmonic, the diagram will be like this. And the third harmonic, the diagram will be like this. So these are the fundamental and the different harmonics. Okay, next we come to standing waves in case of sound. Okay, so far in today's session, we have only been talking about string waves. In today's session, we have not spoken about any other kind of wave. We have only been talking about string waves. Now, the fact is that you can also have sound waves. So, what is the difference between string waves and sound waves? Actually, string waves are transverse. That means the disturbance uh, of the string particles will be perpendicular to the propagation, and sound waves are longitudinal. That means the disturbance will be in the direction of propagation. So, if you are talking about standing waves in case of sound, so there is this very famous activity that is called open air column and closed air column. So first we'll discuss closed air column. So what you have to do is you have to take a air column. Basically, one end will be totally closed. So this end is closed, this end is open, and you will have to sound a tuning fork at the open end. So if you sound a tuning fork, what will happen is that you will get a standing wave pattern. Why? Because when you sound the tuning fork, then the air over here will be displaced to the maximum because it is just near to the tuning fork, and at the opposite end the displacement of the air will be zero because it is totally fixed. So over here you will have antinode, and over here you will have a node, and you know that the minimum distance between antinode and node is lambda by 4. So when you sound the tuning fork, this will be antinode, this will be node, and the distance between them will be lambda by 4. In the second diagram, again I am sounding a tuning fork, and again this time what is happening is that at the open end I am having an antinode as usual, and at the opposite end I am having a node. Again the same thing. So opposite end there is no displacement, it's a node. So I told you that the minimum distance between a node and antinode is lambda by 4, and otherwise in this case this is a antinode, this is a node. So this is lambda by 4 and this is lambda by 2. So this is 3 lambda by 4. And then in the third diagram, this is an antinode, this is a node. So between these two, okay, this is the third diagram, the distance is 5 lambda by 4. So 5 lambda by 4 is the distance between the antinode and the node. This is the third diagram. So that means in the first diagram there is an antinode, there is a node. In the second diagram, antinode, antinode, and node, node. In the third diagram, antinode, 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 node, node, node. So the length of the air column is fixed. So suppose the length of the air column is L. Let us say the length of the air column is L. So in the first diagram, lambda by 4 is L. So V by 4F is L. So F will be V by 4L. This is called fundamental. Okay, this is called fundamental. In the second diagram, 3 lambda by 4 is L. So 3V by 4F is M, so F is 3V by 4F. This is called so 3 lambda by 4 is L, so 3V by 4F is L. So F is 3V by 4L, so this is first overtone. It is also called third harmonic. And in the third diagram, 5 lambda by 4 is L, so 5V by 4F is L, so F is 5V by 4L. So this is the second overtone, which is also called the fifth harmonic. So the fundamental F is V by 4L, first overtone third harmonic F is 3V by 4L, second overtone fifth harmonic F is 5V by 4L. So this is the standing wave pattern in case of a closed air column. So suppose lambda is L, so F is 2V by 2L. So this is the second harmonic first overtone. And the next diagram, 3 lambda by 2 is L, so F is 3V by 2L. This is the third harmonic second overtone. So these are the three diagrams: fundamental, first overtone, second overtone, or you can say fundamental, second harmonic, third harmonic. So this is the details of standing waves due to a air column. Okay, standing waves due to sound in case of air column. Okay, so there is a method of using the standing waves due to sound to find the speed of sound in air. That method is called resonance column method. So what you have to do is that there will be water in a tube. So you drain the water and allow it to fall down to a height L1, and then further drain it and allow it to fall down to a height L2. So all the while there is a tuning fork which is being sounded. So Here, when you hear a loud sound for the first time, so this is the fundamental. So L1 plus d is lambda by 4, L2 plus d is 3 lambda by 4. So d is called end correction. So if you subtract these two, so L2 minus L1 is lambda by 2. So lambda is velocity by frequency. So L1 plus d is lambda by 4, L2 plus d is 3 lambda by 4. So L2 minus L1 is lambda by 2, which is V by 2F. So V will be 2F into L2 minus L1. So this is the formula. V is equal to 2F into L2 minus L1. This is the formula which helps us to find the speed of sound in air. And by the way, in this experiment, why do we use end correction? The reason is that the antinode is not formed perfectly at the open end. It is formed a little above the open end. That is why we use end correction. So L1 plus end correction is lambda by 4. L2 plus end correction is 3 lambda by 4. If you subtract L2 minus L1 is lambda by 2, which is V by 2F. So V is 2F into L2 minus L1. So this will help us to find the speed of sound in air. So we still have a few more topics left in waves. We have speed of sound waves in different mediums. We have intensity and loudness of sound. Then we have pressure and displacement equation of sound waves. And of course, we also have superposition of sound waves. So we have a few more topics left in waves. I think it will not be a good idea to try and club everything into one session. So I think we will quit for today. And the remaining part of waves, whatever is remaining, we will complete it on the next session. So I'll end this session. Okay, I'm concluding the session. Thank you all.